Okay, hi gang. Here's part 2 of the week 7 rational functions assistance. And this is a kind of a dull video, but basically I just want to stare at this page with you that you're going to use as a reference for finishing the rest of the assignment. So if you don't have this in front of you, the steps for analyzing and graphing a rational function, go ahead and pause the video and go download that off of document sharing because you're going to want that in front of you to fill it out with this video. Okay, I'll wait. All right. Okay, so if everybody has this in front of them, on this side of the page we have 6 steps for analyzing and graphing rational functions, which I think is a pretty good presentation, although it's a little dense. It's kind of smashed into one column. And so I want to read through this with you at the risk of boring you to make sure everybody's kind of following what I'm telling you to do here. And then on the other side, I've got one example worked out, kind of like I did on the board in the part 1 of this 2-part video. But I want to follow these steps a little more closely. So basically, this says to analyze and graph a rational function, something that's in the form of a polynomial over another polynomial. I'm calling those P and Q. First, factor the polynomials. Factor the numerator and denominator completely. So when you've got this in its factorized version, then you find the domain of the rational function, which is basically all real numbers excluding the zeros of Q. In other words, anything that makes Q 0, which will be very clear when you look at the factor version, anything that makes Q 0 is going to make the entire fraction undefined and won't be in the domain. So that's a quick way to find the domain. Then you look at the factors above and below. You look at the factors of P and Q and see if there are any common factors that you could cancel in order to simplify the fraction. Usually there are not, but sometimes there are. And in that case, you want to go ahead and cancel those factors and rewrite the fraction in lowest terms with just the uncanceled factors. And then note that any zero of a canceled factor will create a hole in the graph of r of x at the point z comma r of z. This gets a little dense with the function notation, but it's just saying you go ahead and cancel like factors, but if you cancel x minus 3 over x minus 3, that means that at the point x equals 3, at 3 comma, whatever you get when you put 3 in here, r of 3, you're going to see a hole in the graph that's going to be represented by just an open circle that the rest of the graph will flow through, and we'll look at an example like that. Okay. Then, with the rational function factored and in lowest possible terms, you find intercepts of the rational function, and this is like you do for any other functions. The y-intercepts happen when x equals 0, so just r of 0, input 0 to find the y-intercept. And x-intercepts occur when the whole function formula is equal to 0, and if you think about it, that only happens when the numerator is 0. So basically, the zeros of p of the polynomial on top are going to give you the x-intercepts of the entire graph. And the zeros of q we'll use next in looking at vertical asymptotes. So once you find the intercepts, get some points to plot, then you find asymptotes. First the vertical asymptotes, those are the x equals zeros of q. So the zeros of the numerator are x-intercepts, the zeros of the denominator are the locations of vertical asymptotes. Step 5, here we find horizontal or oblique asymptotes. And it'll turn out that these functions will either have a horizontal or an oblique or neither. They won't have more than one thing of this flavor. So it works to find them together, and you do this by analyzing the degrees of the polynomials on top and bottom. You look at the degree of q, p, and the degree of q, rather. If the degree on top is less than the degree on the bottom, there's a horizontal asymptote at y equals 0, otherwise known as the x-axis, if the degree on top is less than the degree on the bottom. Step B, if the degree on the top is the same as the degree on the bottom, if they're equal, then there will be a horizontal asymptote that's found by taking the ratio of the leading coefficients of the polynomial. So, basically the first number you see here over the first number you see here. The leading coefficient of P over the leading coefficient of Q will give you the height of the horizontal asymptote. Y equals that ratio will be the equation of a horizontal asymptote. So that's for a degree on top smaller or degree on top equal. What if the degree on top is 1 bigger than the degree on the bottom? So degree of P is equal to degree of Q plus 1. And I believe I did one of those on the whiteboard. There you can actually carry out polynomial division and you'll get an oblique or slant asymptote. Y equals the quotient of P divided by Q. The last step is putting it all together in graphing. Sketch the asymptotes you find, plot the intercepts that you found, plot a few more key points, consider how graphs behave near vertical and horizontal asymptotes, graph by hand, check by calculator if necessary. Okay, so let's fill out this right-hand column now and kind of go through the steps for a specific example. So I've given the example here of rational function r of x equals 4x squared minus 1 over 2x squared plus x minus 1. Start by factoring both p and q, right? First step, factor everything in sight, right? And then we can see the domain. The domain will be all real numbers except, and we just look at the places where the fraction is undefined, where we're dividing by 0, and the factors help. So x plus 1 is 0 when x is negative 1. 2x minus 1 is 0 when x equals 1/2, or I can solve a little equation setting 2x minus 1 equals 0. So I find that the two zeros of the denominator are negative 1 and 1/2, and the domain of r of x is all real numbers except those two, negative 1 and 1/2. Okay, now I reduce to lowest terms, and I gave you an example here where 2x minus 1 is a factor in both numerator and denominator. You can throw that factor away as long as we realize that we have to think about something special happening at that value of x equal to 1/2, where I'm pitching those guys away. I will get a hole right at x equals 1/2, which means I need to plug 1/2 into this simplified, this reduced version of r of x. Here it is in lowest terms. So I take r of 1/2, I put in 1/2 here and 1/2 here, and I simplify and I get 4/3. So there's going to be a hole in the graph at 1/2 comma 4/3. And if I look down here at the graph I wind up with, what I mean by a hole is an open circle here. It's just a point along this piece of the graph, but it's a place where the function's undefined. So for an input of 1/2, it's actually not even in the domain, right? And at that point 1/2 comma 4/3, I've got to draw a hole, kind of a missing point in the graph. Okay. Continue. Step 3. Find intercepts. R has an x-intercept where the entire function is 0. That's where the numerator is 0. Set 2x plus 1 equals 0. You get negative 1/2. So negative 1/2 comma 0 is an x-intercept. There's a y-intercept when you plug in 0 for x. So I'm just putting in 0 for x right here. 2 times 0 plus 1 over 0 plus 1 is 1 over 1 is 1. 0 comma 1 is a y-intercept. Step 4, getting into vertical asymptotes. The remaining factor in the denominator is x plus 1. That's 0 when x is equal to negative 1. So x equals negative 1 is the equation of a vertical asymptote. Then analyzing for horizontal and oblique asymptotes, we look at the degrees in the polynomial. The numerator is first degree, the denominator is first degree, the degrees are equal. And since the degrees are equal, there will be a horizontal asymptote found by simplifying the ratio of leading coefficients. So the coefficient in the numerator is 2. The leading term is 2x, the leading coefficient is 2, and the leading coefficient in the denominator is 1. So 2 over 1, y equals 2 over 1, or y equals 2, the equation of a horizontal asymptote. Finally, step 6, putting this all together and graphing this stuff. sketch asymptotes. We've got a vertical at x equals -1. We've got a horizontal at y equals 2. Put in the intercepts. 1, 2 points are found from the intercepts. Plot a few more points. I plotted maybe even more than I would need to here, and I graphed a few more points. Plot that hole at point 1/2, comma 4/3, and then put it all together by drawing the parts of the graph that make sense from the asymptotes and the intercepts and the points you found. Okay, not a great video. I hope if you've got this filled in correctly that you'll be able to follow these steps using this example in order to do the analyze all the and graph the rational functions that are on the rest of the activity due on Thursday, and good luck with that. I'll see you in email.